Okay, so a few more questions here that we can go over in this video. An electron is excited from the n equals 1 ground state to the n equals 7 state in a hydrogen atom. So this is you see a hydrogen atom, you see n type problems. This is a Bohr orbital type problem. Which of the following is true? It takes more energy. There's a conceptual problem, right? No problem solving here. It takes more energy to ionize, completely remove the electron from the 7 state than the ground state. Okay, well, if you think about the Bohr model is wrong, but it's correct for hydrogen, but it's wrong for multi-electron atoms. You have your nucleus, right, your positive charge. And then the Bohr model is kind of going back to um, the first problem, right, the true and false, number one. You have these orbits, just like a solar system, okay? Again, this is not what reality is like, but the Bohr model only works for one electron atoms, okay? So this question, A is saying, hey, if you're way up here, you know, in the 7th orbit, and you're trying to eject out into outer space, essentially, that's what eject means, right? Completely dissociate from the atom. That would take more energy than something at the ground state. Well, ground state's n equals 1. So, I mean, just look at the length of these arrows, right? It's going to take more energy because you're closer to the nucleus if you're n equals 1 at the ground state. So definitely A is false. B, the electron is closer to the nucleus on average in the n equals 7. No, by this picture, right, n equals 7 means further away, okay? So that's not true. C, the wavelength of light emitted if the electron drops from the n equals 3 to, that should say n equals 7. Sorry, it's a typo in that key. I fixed it in the exam. N equals 7 to n equals 2 state will be the same as the wavelength of light emitted if the electron falls from n equals 7 to n equals 1. Well, even if it was n equals 3, I think on the exam I put n equals 7. But anyway, both of those would be false because they're different numbers, okay? So if you are going between different sets of energy states, those have different spacings. They're not all the same, okay? And you mathematically could prove that with the Rydberg equation, which was given to you on the formula sheet, but you don't have to do that, okay, to know that. D ends up being the last one and the correct one. The frequency of light emitted when the electron returns to the ground state from n equals 7 will be the same as the frequency of light going from n equals 1, absorbed to go from n equals 1 to n equals 7. Okay, so let's think about this. You have n equals 1 and n equals 7. There's some distance in energy space between them in both cases. And the problem is saying frequency of light when the electron returns to ground state, so you have electron in there. Now you're saying I'm going to go back to the ground state. That's going to be more stable, right? Ground state's more stable than this excited 7th state. So that's going to give off energy. Giving off energy is light emitted. How much energy? Well, whatever this delta E is value, right? Whatever that is, the spacing between those two energy levels. I don't need to calculate it, okay? And now what if I want to absorb to go from n equals 1 to n equals 7? Well, that's the exact opposite process. And what frequency of light am I going to need? Whatever frequency of light has that same energy gap, right? That same delta E. So that's why D is true. All right, which of the following resonance structures is number 8 is the most stable? Okay, so how do you do this? Choosing between resonance structures, remember, is all about formal charges. So we basically just need to go through here. We don't really need to read, you know, A, B, C, D yet. Let's just go through here and calculate the formal charges. How do you calculate formal charges? Formal charge is Fc, just to remind you. It's number of valence electrons minus number of bonding electrons divided by 2, okay, because each atom is sharing a bond, right? It's a covalent bond, so they get half of those electrons. And then minus by the number of lone pair electrons, okay? And so let's just do one explicitly here out. Nitrogen. Nitrogen is in group 5, right? 1, 2, 3, 4, 5. Okay, so nitrogen is in group 5, so it's going to be 5 minus 6, right? 2, 4, 6. Well, let me do bonding electrons first, so we go in the order of our formula here. Bonding electrons, divide by 2. 2 bonding electrons, number of bonds is a number way of saying this. Okay, so 1 bond, and then minus 6, there's 6 lone pair electrons, 2, 4, 6. So that's 5 minus 7, that's minus 2. So this is a minus 2. Carbon, this one is 4, right? Carbon is next to nitrogen to the left here. 4 minus 4 bonds, 8 bonding electrons divided by 2. No lone pairs, 0. Oxygen is 6 to the right of nitrogen, so it's 6 over. 6 minus the 3 bonds minus the 2 lone pairs gets you plus 1. Check your answer here. Did this make sense? -2 plus a 0 for carbon plus the 1 for oxygen should equal the overall charge, which is -1, and it does. Next one. Nitrogen. Group 5 minus 2 bonds minus 4, that equals -1. Carbon is 4, group 4, minus 4 bonds, and there's no lone pairs, so that's 0 again. Oxygen is 6, group 6, minus 2 bonds, minus 4 lone pairs, and that is 0. Does this make sense? Check your work. -1 plus 0 plus 0 is -1. Matches the charge. Last one. Nitrogen is 5 minus 3 bonds minus 2. It's going to get you 0. Carbon is, again, group 4 minus 4 bonds, no lone pairs, so that's going to get you 0. And oxygen is 6 minus 1 bond minus 6 lone pairs, that gives you -1. -1 plus 0 is -1. So we did all of our formal charge calculations correctly. Which one is the most stable? Rules for the most stable formal resonance structures based on formal charges. You want the ones closest to 0. Okay, so this first one's out. A is out. It has a -2. The other ones don't have -2s, right? We have 1s and 0s. Next, deciding between those, you want the one that has the negative charges on the most electronegative atoms, right? Electronegative atoms want electron density, so they should have a more negative electron density, more negative formal charge. So this one, B, you have a -1 on nitrogen. This one, C, you have a -1 on oxygen. So which is the more electronegative atom? Oxygen. It's to the right. Remember your electronegativity trend. Electronegativity increases in that diagonal direction. As you go to the top right of the periodic table, fluorine is the most electronegative atom. So this tells you that C is the best because you got that -1 charge on the most electronegative atom. So that's, it turns out to be answer C. Okay.